Hello and welcome to this tutorial on a frequency analyzer, one of the key features present in many plugins from MeldaProduction. We can find it in all equalizers, crossovers of multiband effects, and of course in M Analyzer and M Multi-Analyzer. As with many other features, this one is packed with parameters, modes, etc., and yet you don't have to be a scientist to successfully use it. In this tutorial, I will uncover everything you need to know about the analyzer. For my demonstration, I'm going to use a mighty M Auto Dynamic Equalizer. If you haven't tried it, I suggest you do that as it can satisfy all your equalizing needs. The analyzer is situated right in the center of the plugin. To activate it, click on the Analyzer button. Play some music. From the very beginning, it may seem cluttered with information. A constantly changing graph, readouts, a rainbow-like stripe at the bottom. It's rather a demo of what the analyzer can show. I'm going to turn off some features and we'll start explaining things one by one. So what is this green jumping curve? It represents a frequency response of an incoming signal. It's achieved by utilizing the Fast Fourier Transform Algorithm, or FFT in brief. I'm going to omit all science and just to mention that this algorithm breaks a signal down into sine waves with particular amplitudes and phases. And this is what these vertical peaks represent, the amplitudes of those sine waves over a frequency range. You may ask, why do the peaks on the left side look thicker than those on the right one? You see, FFT algorithm wasn't originally created for audio signal analysis, and this is the result of the FFT algorithm's adaptation to the way we perceive a signal's pitch. Our brain analyzes pitch in logarithmic scale that you can see on the bottom axis. However, the FFT algorithm works in so-called linear scale. The analyzer needs to transform one into another, and this is the payoff. As a consequence, the FFT analyzers have worse resolution in low frequencies than in high ones. All settings that we're about to study are for making the data easier to interpret. And the first parameter that can lighten the graph reading is the smoothness. It smooths out the graph. When it comes to perceiving sound, we assess rather a spectrum envelope than single harmonics. And this parameter attempts to do that by smoothing out the original sharp image of the frequency response. However, it's important to understand that it is not a level averaging. That's why the harmonics at the end of the frequency range, that look sharper, get smoothed out first. So yes, this parameter makes the graph easier to read, but it doesn't approximate the graph the way we perceive sound. Now, let's open the Analyzer Settings window. At the very top, we can see a button for opening the preset browser. Here, you can save all settings that can be loaded later into another plugin's analyzer. Lower, there are 5 tabs: Main Settings, Analysis, Graphs, Sonogram, and Prefiltering. Each of them holds a group of parameters. Let's start from the View panel on Main Settings tab. At the top of the tab, there are 4 buttons: Enable, Freeze, Normalize, and Reset. They duplicate buttons on the main window: Analyzer, Pause, Normalize, and Reset, and correspondingly, they have the same functionality. The Freeze temporarily stops the spectrum calculation. The Normalize function normalizes the frequency response graph so that the current loudest peak is always at the 0 decibel level. This mode can be handy when comparing 2 static spectrum graphs. However, at live signal monitoring, it can be very misleading because now the entire graph position depends on the current peak. Compare the graph's behavior when this function is on and off. The Reset button resets the analyzer to its default state. We'll need it when working with specific types of analysis. The view type sets the way the graph is displayed. At the normal setting, the graph is shown as the usual FFT graph that you can see right now. This mode is great for searching some anomalies as it's very detailed. However, because it presents so much information, it can be hard to interpret. If I turn on the 1/3 octave mode, the graph will be presented by vertical bars. The width of each bar is equal to 1/3 of octave, and as with the smoothness parameter, we observe one more way to generalize the frequency response. The level of the bar corresponds to the highest peak within the band. As you can see, the amount of the information got considerably reduced in comparison to the normal mode. Hence, an assessing of the spectrum became much easier for eyes. The next button to the right is the 1 octave. It does the job similar to the 1/3 octave mode. The difference is the frequency range is divided by the 1 octave regions. The opacity slider adjusts the opacity of the graph. It doesn't influence the frequency response in any way. It simply helps you to set its appearance. The resolution defines the level range of the analyzer. The values of the resolution are found on the right side of the main window. For most applications, the default value, -60 decibels, should do. However, if you'd like to check really quiet signals like dithering or aliasing, you need to increase the resolution. The next panel down is the analysis, and the first parameter we're going to discuss is the source. Here we select the signal whose frequency response we want to see. The options are input, output, input and output, and side chain. Because we're dealing with the equalizer, the most useful option would probably be the input and output, as it allows seeing the effects of the equalizer settings in comparison. The M-Auto Dynamic Equalizer wouldn't be one of the most powerful equalizers if it didn't have a sidechain input. The sidechain option makes checking the sidechain's input signal possible. In the following example, I'm going to check a solo piano spectrum to make a whole in a mix for it later on. Thus, if I'm going to dynamically control M-Auto Dynamic Equalizer on the instrumental track, I don't have to insert one more instance of M-Auto Dynamic Equalizer into the piano's track just to find out its frequency response. I can easily do that in the same plugin by selecting the sidechain input here. Simple. The channel mode chooses a channel we'd like to analyze. We can select the left, right, mix, that is a mix of the left and right channels, and left and right. In the last case, we will see both channels simultaneously. Note, the analyzer can show maximum 2 graphs in real time. So if you set the input and output as the source and left and right as the channel mode, you won't see 4 graphs. Averaging. This is one more controller to average the analyzer's behavior, but this time we're talking about how fast it reacts to the change. The higher the value, the slower the response. Any rules here? No, actually. But remember, if you go too slow, you'll start missing short percussive sounds, like drums for example. This parameter affects both rise and fall times of the graph. The decay is responsible for how slowly the graph falls down. The higher the value, the slower the fall. However, the previous parameter, averaging, has a priority here. The decay adds an extra time to the fall set by the averaging. The Super Resolution mode provides a high resolution frequency response even at the low bottom. Usually when we want to have a good resolution at low frequencies, we have to increase the total resolution of the analyzer. That slows down the analyzer's response time. This mode keeps a quick response at high frequencies and, at the same time, it considerably improves resolution at low frequencies. The enable when hidden keeps the analyzer working all the time, no matter whether the plugin's user interface window is opened or not. This option is useful if you want to see a sonogram straight away after opening the plugin. Moving to the Analysis tab. Here we find settings related to the analysis itself. The slope controller tilts the spectrum. Let me explain the reason to have it. You see, the FFT analyzer shows true amplitudes of signals. It's useful information for mathematical analysis, but again, it doesn't correlate with the way our auditory system assesses the loudness. The power of the signal in frequency bands is much more useful to this purpose. In the past, mixing engineers used analog analyzers in which 20 Hz to 20 kHz range was split into 31 sub-ranges, each of 1/3 octave bandwidth. Those analyzers displayed a row of equal height bars if a signal with an equal power in each band, pink noise, was played back. So by looking at the analog analyzer, an engineer could judge the power of the signal across the full frequency range, not the amplitude of harmonics. This analysis correlates with our auditory system much better. Now, back to the FFT analyzer. If we play back the pink noise, the analyzer will show it as a falling line. We can make it horizontal by setting the slope to +3 decibels, and thus emulate the behavior of the analog analyzer. Moreover, you must put a +3 decibel value here if you use the 1/3 or 1 octave view type we discussed before. It's also a useful feature to judge relative amplitudes between harmonics. For instance, if I'd like to see what the flanger effect does to the saw wave, I'd rather put +6 decibels here to get all harmonics at the same level. And now, judging the effect is much easier. As we're discussing the graph slope, I'd like to introduce you to a similar but much more powerful feature, pre-filtering, on the last tab. This is something no analog analyzer can touch. Here, we can literally draw a target spectrum shape by utilizing a powerful shape editor. And when the actual signal spectrum coincides with it, the analyzer will show a straight line. This is how it works. First, make sure the slope parameter is set to 0. Next, draw the target shape. Now close the analyzer's settings window. Play back some music and use the equalizer to match the music spectrum to the target one. This method will suit to those who like using a reference curve, for example, ISO 226-2003 or Fletcher-Munson. I wouldn't trust the local presets though, they are very loose. Sure, Wojtek did his best, but his drawing skills are not so good apparently. I've heard his drumming is much better. Obviously, you can come up with your own signature curve, so when you mix to it, your mixes will have more or less similar balance. That, in turn, will make mastering much easier. The slider on the top adjusts the depth the target curve has on the analysis. So, why a straight line looking spectrum anyway? Because referencing to a horizontal or vertical line is much easier than to a slope. For all details about the shape editor, please watch the Graphs in MeldaProduction audio plugins tutorial. Now let's get back to the Analysis tab. The gain controller shifts the graph vertically. It works as if we change the signal's level. Convenient when you're dealing with low-level signals. It can be a good alternative to the normalize function because the position of the graph doesn't depend on a current peak. This function is cancelled if the normalize is on. The time resolution improves the time resolution, useful for quickly changing signals. The deharmonize tends to remove harmonics and to leave only fundamentals. It can help you to determine the most prominent frequencies in the signal. The peak detection and peak threshold are parameters controlling the peak detection function of the analyzer. It adds a readout with a frequency and note values to the first 4 highest peaks. The first parameter works as a harmonic amplitude expander, pushing low-level signals even lower. And the second one sets a threshold for the low-level signals. If the level is lower than the parameter's value, the harmonic will be suppressed. Moving to the scientific settings. To understand these parameters, we need to know how the FFT analysis works first. I'll try to make it as simple as I can. For example, this is part of an audio track we'd like to analyze. What the FFT analyzer does is, it takes a chunk of audio, analyzes it, and depicts the result as a graph. Then it takes the next chunk, analyzes it, and depicts the new graph, and so on, till the end of the audio track. Thus, the FFT analyzer processes audio step by step, and because it happens very quickly, we can't really notice these steps. Now, if you've edited the audio, you know that you can't cut off a waveform any way you like, because there's a good chance you'll get a click. And to avoid it, you should look for a place where the waveform crosses the time axis at 0 decibels. And this is where you must cut off the waveform. If you do that, you won't get any clicks. But what has it to do with the FFT analyzer? You see, if the analyzer recklessly cuts off audio into chunks, each chunk will have a click at the beginning and the end. As you probably know, a click has a very broad spectrum, and this spectrum will be added to the spectrum of the chunk. As a result, the analyzer will print a different result in comparison to the actual one. To avoid that, a decision was taken to apply a fade in and fade out to each chunk of audio. That's good, but now we've got zones where the signal is missing. To fix that, the chunks should overlap each other. Now, all answers. The size of the audio chunk is defined by the FFT size parameter. It's expressed in samples. For example, 4096 size is equal to 92.88 milliseconds at 44,100 Hz sample rate. The shape of the fades is determined by the window type parameter. It also defines the way peaks are presented on the screen. If you're really interested in knowing the difference between them, you can easily find this information on the internet. The size of the overlap part is set by the overlap controller. 1 times means no overlap. 2 times stands for 50% overlap. 4 times for 75%, and so on. The default 4 times setting works just fine. The analytical smoothing mode turns on an alternative mode to smooth out a frequency response. It works in conjunction with the smoothness parameter we saw on the front panel. If lit, the high-frequency harmonics won't get suppressed as hard as they would when it's off. This mode consumes more CPU power. The Graph tab. Here we select types of graphs we want to see, and to see them we must click on the corresponding Enable button. The first one from the top is the average. Right choice when you need to see a signal spectrum in real time. It is also the only type whose time properties can be set by the averaging and decay parameters on the main settings tab. For classic RMS, like ballistics, try values between 160 and 200 milliseconds for the averaging, provided the FFT size is 4096. And for the decay, any value that pleases our eyes. The next one is the average, infinite. Apart from the previous type, it shows a static graph representing the average level of the signal for as long as it is present. Besides the levels, this type takes into account the duration of loud and quiet parts. The longer the loud parts, the higher the level. In the following example, I have 2 modulated sine waves. Their maximum and minimum amplitudes are the same, shown in black. However, the wave on the left stays at its maximum twice as long as the wave on the right. As the result, the average, infinite level for the left wave is higher than the level for the right one, shown in green. The following is the maximum type. This graph shows a current maximum value. Its reaction time is very fast and the decay is reasonably slow, so it's easy for eyes. The maximum infinite spectrum displays absolute peak levels for the analysis time. Again, it is rather a statistical tool. The last graph is the maximum minus average infinite. This type was created as an experimental one to access a signal's dynamics. It takes the values of the average infinite and subtracts them from the maximum infinite. To use it in the right way, set the slope to 0. Play some music and let the graph settle down. Now we need to identify areas where the graph has different level zones. So what can we see here? The range from 100 to 2500 Hz has more or less similar values. The range from 20 to 100 Hz has a distinct hole. And we've got two peaks approximately at 4.1 and 10 kHz. Great! And what's the use of it? Well, it can suggest a crossover band, for instance. Here is how I split it. The logic is to unite areas with similar levels under the same band. In the case of those two peaks, perhaps a dynamic equalizer is a better choice if they cause a problem. Important, this is not a dynamics analyzer. This graph is to give you only an idea about a signal's dynamics across the frequency range, so don't take it as a measurement tool. You can always reset any analyzer by clicking on the Reset button on the main window. The last option on the Graphs tab is the Comparison. This is not an analyzer. We can call it a memory slot for storing any of the above-mentioned graphs. To use it, choose the graph you like and click on its Copy Analysis button. Next, click on the Paste Analysis button. Now that graph will stay on the main window until you disable the comparison. Handy feature if you want to compare a frequency response before and after processing. You can also do the same actions straight on the main window. These two buttons in the top right corner have exactly the same functionality. The first one is for copying and the second button is for pasting. The difference is, on the Graphs tab, you can copy any graph you like. However, on the main window, the preference is given to the first from the top graph. For example, if you've got the average, infinite and maximum graphs enabled, pressing the copy on the main window will copy the average graph. Each graph has 6 options. The track peaks turn on the numerical readouts of the 4 currently highest peaks. You've already seen the microsonogram at the bottom of the main window. The thick makes the graph use a thick line. If you prefer a filled look to a single line, click on the Fill Area option. Finally, the Color allows you to use the color from the color editor instead of the default one. One more button I must mention here is the Fill on the main window. When on, the microsonogram is shown over entire analyzer screen. The sonogram enables the sonogram. The sonogram codes levels by colors. Let's open its tab. Here, we set a range of colors that are used in the sonogram. The very left color corresponds to the silence, and the very right one to the maximum level. Plus, we are given 3 more colors between them. To create your own color gamma, simply click on these buttons and select the color you like. In the preset menu, you'll find quite a few presets already made for you. Of course, you can save and load your presets as well. I need also to mention the overlap parameter on the Scientific Settings panel. It regulates the sonogram's pace. We've finally come to the end. As you can see, the FFT analyzer can reveal lots of information about your audio. At the same time, we must understand it doesn't present data the way we perceive sound. It's a good assistant. However, you come first. I hope you found it useful. Thanks for watching.